Hey everybody, so in the last few videos we've been talking a lot about how we do statistics with population proportions. We talked about sampling distributions for proportions, confidence intervals for proportions, and ultimately inference on proportions. So obviously there are more things we can look at about populations than the proportions that fit some certain demographic. So we're going to start talking about doing statistics on means, population means. So just like with proportions where we started with sampling distributions, we're going to start with sampling distributions for means. So let's start with a refresher on how we compute sampling distributions for proportions. The purpose of this is to show you how similar the process of finding sampling distributions for means is, and also highlight where the differences are. So when we're working with a population proportion, we call the population parameter P, if you recall, P for proportion. The sampling distribution shape was always assumed to be normal, and the mean of the sampling distribution was found to be P, exactly the same as the population parameter. So the sampling distribution was centered on the parameter. The standard deviation of the sampling distribution depended on n, and it came out to this, the square root of P times 1 minus P over n. So let's look at a couple practice questions to remind ourselves how we actually did computations on sampling distributions for proportions. So suppose it is known that 11% of all people are left-handed. If a random sample of 100 people is taken, what is the probability that the proportion of people in the sample that are left-handed is between 9% and 12%, less than 7%, or greater than 14%? Before we go into the process of solving this problem, I want to see if you can predict which of these answers from 1 through 3 would be the highest probability and which one would be the lowest. Remember that the parameter, the actual proportion of people who are left-handed, is 11%. So let's take a look at how we would solve this. We know that the sampling distribution will have a mean of 0.11 because that is the parameter, 11%. In order to find the standard deviation, we would have to bring out our calculators, and I'm going to do the square root of 0.11. I know that 1 minus that is 0.89, and that's divided by 100 under the square root. And that gives me 0.0312, so on, so on. I'm going to round that to 0.0313. So in order to compute our first result, we're going to use normal CDF. Our left bound's 0.09, right bound's 0.12. Our mean is 0.11, and our standard deviation is 0.0313. This gives us a final probability of 0.364. For less than 7%, since we're doing, that's a left tail, our left bound's going to be negative infinity, our right bound's going to be the 7%, our mean and standard deviation are the same, and that comes out to about 0.101, a little more than 10%. And finally, greater than 14%, since that's a right tail, our upper bound will be positive infinity, but our left bound will be the 0.14. Our mean and standard deviation are the same. So you should have been able to predict that number 1 would be the most likely and number 2 would be the least likely, because number 1's question was centered around the mean, which has the greatest probability of occurring, while 7% is much further from the mean of 11% than 14% is. So 2 should be less likely than 3. So let's talk about sampling distributions for normally distributed means now. So for a sampling distribution for normally distributed means, to see how it actually works, I'm going to bring up a little applet here. And so this is taking a look at, let's say I have, this is my parent distribution. It's normally distributed, and according to this applet, it's drawing it to have a mean of 16 and a standard deviation of 5. So here's how this applet works. It takes samples of certain sizes from this population and computes what the mean is. So for example, here in this area, I will be drawing the sampling distribution when the sample size is 5. And here it's going to draw it when the sample size is 25. So there's this cute little animated feature that actually shows it taking a sample. So there it's taking a sample of 5, and it did the mean there, and now it's taking a sample of 25, and it's going to put the mean down here. So that's it, just computing one sample with one mean. Now that doesn't give us a distribution, it gives us one value. So I'm going to fast forward this process, and I'm going to have the applet do this 100,000 times. So here it will draw the distribution for 100,000 samples of size 5, and here will be 100,000 samples of size 25. So let's do that, and let's see what it does. Okay, so it drew them out, and we should notice a few things. For one, both of these sampling distributions are centered at 16, which is exactly the same as the center of our parent. But both of them also are following a pretty normal shape. Right here the app is actually drawing in sort of a bell curve to fit it, but they both have this sort of bell-shaped look to them. However, the big difference between them is that the sample size 5 has a much wider spread than the sample size of 25. And in fact, if you notice, the standard deviations here for 5 is 2.23, and for 25 it's actually 1. So from a standard deviation of 5, we got to about 2.23 when the sample size was 5, and 1 when the sample size was 25. So it seems like for means, the sampling distributions will have the same center as the parent. Here they're centered around 16, which is the same here. And the standard deviations will decrease as the sample size increases. So what does that actually end up looking like? So the population parameter here, the mean of the population, we actually give it the symbol mu. For proportions we call it p, but for means we call it mu, which is really kind of like just a lowercase Greek m. The population standard deviation is given the symbol sigma. Now we've used these before in doing normal curves, so these symbols should be familiar to you. The shape of our sampling distribution, as we saw, is going to be normal. The mean of the sampling distribution, if you saw there, they were both centered right where the population parameter is. So the mean of the sampling distribution will always be mu. And the standard deviation for a given sample size is going to be the population standard deviation, but divided by the square root of the sample size. Now, that actually worked out very well in the applet that we were looking at, because originally the standard deviation was 5 in this example, and when the sample size was 25, it became 1. So the square root of 25 is 5, so 5 divided by 5 is 1. So it actually worked out very nicely when we had 100,000 samples here. So the reason why, again, I wanted to show the sampling distributions for proportions is to talk about what these types of sampling distributions have in common. So whether we're talking proportions or means, both of them have a normal shape to them. Both of them will be centered around whatever the population parameter is, and both of them have the property that as the sample size n increases, the standard deviation of the sampling distribution will decrease. So a larger sample means a more tight distribution. So let's take a look at a practice problem that uses a sampling distribution for means. So let's say the heights of adult men are normally distributed with a mean of 70 inches and a standard deviation of 4 inches. We will now assume that a random sample of 50 men is taken. So the first question is, what is the shape, center, and spread of the sampling distribution? So we should get that because the population is normal, the shape will be normal. The center will be the parameter, which is 70, but the standard deviation is going to be different. I can find it by doing our population standard deviation divided by the square root of our sample size, which in this case is 50. And that tells me it's about 0.5656, or I'm going to round that to 0.566. So it's centered, the same as the population, but the standard deviation is smaller because we're taking a sample of 50 men. What is the probability that the mean of the sample is between 68.5 and 70 inches? Well, again, since this is a normal curve, we're going to use normal CDF. Our left bound will be 68.5, our right bound will be 70. Our mean is 70, and our standard deviation is 0.566. You could do that on your calculator. It comes out to about 0.496. Finally, what is the probability that the mean of the sample is greater than 72 inches? And again, that's going to be our normal CDF. Right is positive infinity since it's greater than 72 inches. Our mean is 70, and our standard deviation is 0.566. And that gives us a probability of 0.0002, which is very, very small. Now that should make sense because the population mean is 70, and we're taking a pretty big sample of 50 men. It's very likely that the mean of that sample is going to be pretty close to the population mean of 70. 72 inches is actually a decent amount away, so the probability it's going to be that far away is going to be pretty small for a sample that big. So one other thing I want to talk about, and this is actually really, really important for statistics, so we're really just touching upon it here, but when the population distribution is normal, the sampling distribution will also be normal as well. And most of the distributions we will look at are going to have normally shaped populations. The height of all men is normally distributed. But what if the population distribution is not normal? Because there are plenty of distributions in the world that don't have a beautiful looking bell curve. So we can actually take a look at that. So I'm going to change my parent population here to be skewed. And you can see here this is a right skew since the tail is off to the right. All right, so now I'm actually going to, if we could animate these means here just like we did before. There's a sample of 5, and now it's going to do a sample of 25 for the bottom. Getting my sample. And there it is. So not surprising, larger sample. The mean of the value is a little closer to the center here. But what happens if we do this 100,000 times? Let's take a look at these sampling distributions. So take a look here and look very, very carefully. They both look pretty bell-shaped, but take a look at the smaller sample size. The smaller sample size produced a distribution that's still a little bit, the mode is still, the mode is still a little bit to the left here of where it would be on the normal curve. So there's still more of a right skew here. But when the sample size is 25, that seems to be reduced a bit. It looks more symmetric than it does here. So that's actually a really important point. So when the sample size is sufficiently large, the sampling distribution will tend to be normal regardless of the shape of the parent distribution. This is actually a really important idea because sometimes we don't know what the parent population looks like. But this tells us that if the sample size is big enough, we could still treat our sampling distribution as being normal. This idea bulleted here, is actually called the central limit theorem. It's one of the most important theorems in all of statistics. Sometimes it's affectionately abbreviated as CLT. Now what this doesn't say is what sufficiently large means in terms of a sample size. And the reason why I didn't put that down is because technically that sort of depends on what the parent looks like. But for many situations, a sample size of at least 30 is typically big enough where we don't even really care what the parent population looks like. We can assume the sampling distribution is normal. So at least 30 is usually good enough for the central limit theorem to work. Now again, most of the distributions we'll look at will have normally shaped populations, but this is a really important point. Really, if this theorem were not true, statisticians couldn't do a lot of the work that they do. So I didn't want to go through this video without mentioning it because it's kind of important, but it's not going to impact us too much in the examples you're going to have to work on, but I just didn't feel right doing this without bringing it up, at least at the end. So That's it for sampling distributions for means. And next time, on the next video, we will look at confidence intervals for means.